Okay. Hello, I'll talk about making music with a C compiler and introduce libglitch, which is a synthesizer software I've written. I'm going to explain something that defies the contemporary approach to digital music synthesis, which is that people either use stuff like digital audio workstations, like many digital audio software resembles multi-track tape recorders. You probably know Audacity or even more weird software. Or that people use MIDI sequencers and trackers, which mean that they have notes on monophonic channels. For example, play this note, play this note, play this note on a piano. Or loop-based stuff, where when people program their drums, even people who can't really program do that for percussion instruments, or people use samples and loop them. Because all of these have principles in common that are not strictly necessary, which are having notes for a melody, having instruments or channels in the case of the multi-track tape recorder, and having an explicitly denoted score. And we actually don't need all of this. But what is interesting is that however diverse the interfaces are for audio software, all of them exhibit, regardless of the approach, almost all of them, because I will explain one that is different, exhibit this reliance on notes or a melody, instruments, and having a human noted score. This is Pro Tools. You see what I mean with the multi-track tape recorder metaphor. It's people have samples and order them, cut them, play them faster or slower, but ultimately it's up to the human to decide how the composition works. And this is Reactor, which has both imitate of a physical workstation, which you can see above on the left and right side. I have actually no idea what they're doing, and has flow graphs, like directed graphs for sound synthesis, which may or may not resemble what people can do with the interface above. And maybe some of you know the trackers, which is software that looks suspiciously similar to a hex editor. People edit tables in which they have a note, an effect for the note, and channel or loudness information. For example, in this case, you have 12 channels, and they play different sounds on different instruments. And in the middle, below, the samples are listed, which are used for that. And on the right side, you can see how the volume is controlled. And on the left side, you can see how loud the channel currently is. And then it goes from top down and plays them after each other, notes and channels, making a melody. I have no idea what this is, but it exhibits the case that I think every metaphor can be used interchangeably in some way if you just know how it maps to this notes, tracks thing. Like you can make a score with your drum computer if it only has physical buttons. You can draw the waveform with your cursor if you want, or you can, I don't know, record stuff and play it simultaneously and repeat. Besides these graphical interfaces, there are also domain-specific languages. For example, C sound. I have no idea what this is doing, but it's out of Wikipedia, and apparently, if you look at it, it also notes how the instrument works and what the score is. So you first define an instrument and then define a score. If you don't do this, for example, in Super Collider, you're reduced to pure waveforms, and this is what I want to go to, but without a domain-specific language, but with a general-purpose language, which is C. When I looked for this lecture for sound that does not rely on instruments and nodes, but that is generated by something that resembles more C code than something else. I finally found that the deep node from THX is a very common example where people are not able to identify instruments, and it sounds like that. So Wikipedia also says that behind that there are 20,000 lines of C code, which output 250,000 statements of the form set oscillator X to frequency Y for the audio signal processor, which the guys had to make that demo, which is now in front of many movies. But if you compare this to contemporary software that solves real problems like diode libc or Gatling or Fefus block or the ISC client EE, you can see that 20,000 lines for such a simple sound is actually load. And because of that, I want to talk about how to write small and fast audio synthesis software. And the most basic principle is throw away any notion of instruments and of a score and of nodes and just generate a byte stream and interpret it as a waveform. Now, we can generate byte streams. Probably some of you are doing cryptography and have to do this for some or another purpose, which has nothing to do with my purpose. But if I want to have a sound out of a byte stream, I use pulse code modulation, which I will explain. It's that I store the signal magnitude per a specified sample interval, which means that I quantize the signal, and in red you can see a waveform. This is also from Wikipedia, but I've forgotten where. I think the article on pulse code modulation. You have the red waveform, which is the analog wave, which I want to store, and we have a sample interval, which is denoted below, and every time I sample that signal, I store what the magnitude of the signal is. And you can approximate this to, if you had a speaker, how the membrane would vibrate. The interesting thing is that you can almost always, by simple approximation, turn the digital signal, the black jagged line, back into the analog signal, the red line. You just need to do some filtering stuff, like remove high frequencies which are introduced, or introduce some noise before encoding. This is beyond the scope of this talk. The point is, it's a very easy process. But you have to know what in there affects audio quality. First, we have the bit depth. Like, how many bits are we storing in a single sample interval? Like, you could either have 1 bit, for example, then you can only store is the signal on or off, or you can store more. And chiptunes, for example, 8-bit music. This means that they have only a range of 8-bit, meaning 256 signal magnitudes that they can show. So it's not possible, for example, to have very subtle effects because it has to lie on that scale. The digital video stuff has 12-bit, and audio CDs have 2 16-bit channels. Now I tried to make an example for that, but it's actually inaudible with all the stuff I found, because, well, the dynamic range gets interpolated either from the audio equipment or from your psychology, even if it is not there. Like, for example, if any one of you, next examples, is talking on the phone, they are not consciously perceiving that it sounds really bad compared to audio CD quality. But the second thing is, how often do I sample? The sampling frequency determines what the maximum frequency of the sample, which I want to store, is that I can faithfully reproduce. I have no idea of the mathematics behind that, but the thing is that you have at least be able for a given waveform to store whether in a sample interval where it is not on and where it is on, where it's down or up. So if, for example, you want to reproduce a 4 kilohertz signal with a sampling frequency of per second, 1 hertz, you're just not able to do this faithfully. Like, you can't. So half the sampling frequency is the maximum frequency that we can reproduce. And because of this, CDs, audio CDs, use 44 point, oh, well, there should be a point because it's in English, 44.1 kilohertz, which means that half of that is just above the upper end of the human hearing range. And I will now play something. It's low contrast. I have no idea this presentation program does this. I will something that is synthesized a chart with SOX, an audio tool for command line, with a sampling rate of 44.1 kilohertz, and it sounds like this. Yeah. So if we go lower, common voice over IP sampling rate is 16 kilohertz, because, well, they only need to encode human speech, which doesn't have that many high frequencies. Like the most faithfully reproduced frequency in here is 8 kilohertz. So listen to that and compare it to the thing that I did before. Sounds duller. And obviously, that is because the sample rate is low. The only thing that is different between those two, it's very low contrast, because those two commands displayed at the bottom is that one has a sampling rate of 44,100 hertz and the other one of 16,000. So let's go to the phone. Phone has 8 kilohertz, maximum representable frequency is then 4 kilohertz. So listen to this and compare it to the previous two charts. Sounds very dull, and this is why you don't play some music over the phone unless it's, well, really low fidelity music. So now, probably many of you have heard of DEF DSP. I hope so. But DEF DSP, which is available on most operating systems except for Windows and OS X, so use a real operating system if you want to do this, is a device that is an 8-bit, 8 kilohertz sync for bit streams, or, well, byte streams, which are sent directly to the speakers of your hardware. Which makes it very easy, because then now our programs only need to concern themselves with generating the byte stream. And this is a very simple program, one of the simplest programs that can generate music. And I don't know how many of you know C codes, but is there anyone among you who cannot program? Okay, there's no one among you who cannot program, so I'll just explain. The include header does something, I think, that gives me the putchar function. I hope so. The main function is the function that is denoted between the brackets, and it has an integer t, which it increments and outputs the last 8-bit, commonly a byte, but I say octet because a byte, well, could be anything, and loops. And if we look at what it outputs, then we get 0, 1, 2, and after it reaches a full byte maximum value, it loops again to 0, because we have an overflow, so we need to think in modulo arithmetic. Every audio signal that I get out of a simple white counter, like an ever-increasing variable, a linear function, must be taken modulo 256. So the blue line that you see is the counter, and the green line is the signal that we get from DEF DSP if we pipe the output from the previous program to that. which means we have a sawtooth wave, which is called exactly like that because it looks like 4 teeth. So the question is, what sound does it make? We can get to that result if we find out what the period of that is and what the sampling frequency is. And we know the sampling frequency, and we know the period because it loops after having put out 256 bytes. And this means we have a sawtooth wave of 31.25 hertz, which is at the lower end of human hearing range, and it sounds like this is 3 seconds of sawtooth wave. Yes. So getting from that to real sound requires that we rethink how we use arithmetic and how we use the C compiler to produce the appropriate byte stream. And which means that somehow our computational primitives like addition, multiplication, bit shifting, or bitwise operators become weird musical primitives. For example, addition or subtraction introduces a phase change in the signal. You can see this here. This is the original counter, and I've added 128 decimal, well, 0x80 hexadecimal, to it, and change the phase of the signal. This is inaudible, but you see we can change the waveform pretty easily, and this is the modified program piped through DevTSB. This sounds like this. As I said, it's inaudible. The dark pink thing there is the modified wave. The green thing is the original wave. It just starts differently. So more interesting is using multiplication or division for frequency changes. And that means, for example, multiplying the counter. Blue is the original counter. Green is the signal if we only output the last 8 bits of the counter, and the wave that is in front of every other is the counter modified by 4 and then taken the last 8 bits, which is actually audibly a frequency that is higher, and because the relation is linear, it's, I think, 125 hertz. So, a guy called Wisnud has done more research into this and has put down a table how you can have traditional nodes and what multiplier you need to use. You can use this for cheating if you want to have a specific frequency. I won't use this except for in one case, which I label cheating, but actually you can get several octaves, but only in the highest octaves you can get many useful tones. But you can actually, if you repeatedly afterwards multiply with the sawtooth wave with different integers, you can pitch it to get higher frequencies than the 31.25 hertz wave that I demonstrated with this simple linear counter. And of course, bit shifting also introduces a frequency change, and this is because bit shifting by 1 to the left means that your integer is multiplied by 2, approximately, because, well, it can still overflow. And bit shifting by 1 to the right is approximately dividing the integer by 2, and it can still underflow, and then you've lost some fidelity. But let's not concern ourselves with that. It just means that this is the same as a multiplication by 4, I think. Sounds the same. So now if we have modular arithmetic beyond the already demonstrated scope, we can make a filter that changes the period and only lets stuff of some, I think, lower frequency through, I'm not entirely sure that this is a low-pass filter because it does work differently, but here you see in green the original signal, in blue the counter, which only goes up linearly, and in pink the modified signal. If I take t modulo something, you see the period is shorter, and I think this means that the frequency is higher. And it sounds like this. So, to actually achieve something with that, because we have just only changed the pitch, actually achieve something that we need bitwise operators, all of them, and apply them to our counter. And with that, the first thing that we can do, the most simple thing, is square wave extraction. Because if you think about it, the sawtooth wave that we saw at the beginning actually consists of multiple square waves overlaid on each other, a square wave for each bit that can be on or off. And I can demonstrate this, for example, by just extracting one bit. Now the pink thing is the square wave I extracted from that, which you can see has a very simple relationship to the green original output value. It just is off when that value is, when the bit is not set, and it's on when the bit is set. It sounds like this. Which is different than the sawtooth wave. You can actually hear if something is a sawtooth or a sine or a square or a triangle wave, which is pretty interesting, but only gets relevant, only becomes relevant later. This is when I take another bit, which gets set and unset more often, 4 times per original wave, which means we now have this. And with this frequency, I think you can probably know that many waves that you know as simple Finty waves are square waves. Now, if we take multiple bits, we can overlay several square waves and to a specific degree approximate a sawtooth wave, but still have some kind of fractal patterns in there. This is T with bitwise AND with 42, which in binary means that there are several overlaid square waves. And it actually looks interesting and sounds like this. And I think this actually starts to appear multitonal because you can hear that this is not just one harmonic. There is a different signal overlaid on the original signal. And going from that, we can start weird shit. For example, changing the amount of modulation by having T, a bitwise AND, with T bit shifted 4 to the right. So the original square wave gets combined with a slower version of itself. And you can see this, the pink line actually shows different patterns, and as the counter goes up, it repeatedly approximates a louder sawtooth wave, but in between there is a sawtooth wave becoming more unruly. And this sounds like this. Which is, for this low complexity software, surprisingly interesting. And even more surprising it has become if you increase the amount of bit shifting a little. This is one of the melodies that everyone that actually tries this approach gets to sooner or later, and it's called by Wisnud, the guy I mentioned before, who has written an article about this, Sierpinski harmony, because it's a fractal. It's actually a Sierpinski fractal like this this triangle, Sierpinski triangle, and on the top you see the fractal and the bit pattern that actually gets output by this program. And at the bottom you see the mapping from the table earlier to actual tones, but I play it again, it doesn't really have notes. And because we actually perceive this single bit stream, this monophone audio, we perceive it, the fractal nature in that, and actually try to explain it. It appears that as if there are different tracks overlaid. And I won't demonstrate all the other primitives because you can learn about this by experimenting yourself, but I have a simple showcase. The first is a Philip Glass simulation, like the composer Philip Glass does music that sounds very fractal, which is this. And it goes even faster and goes up and down until it reverses course because some counter overflows. But what you can see, what I have done here is taking the original square wave, multiplied it by the square wave divided by 6, which is a frequency which is so low that we can no longer hear it, and bit shifted that, using it as a period, as a counter, and then done a bitwise AND with an even slower version of the original square wave, t divided by 12, and which is also bit shifted. So going from that, we can pretty easily do multi-track bit shifting. This song here has, before I play it, I explain it, has 3 different tracks and a snare drum, which are all made of this simple structure of taking a square wave, multiplying it by an integer to get a different pitch, and then bitwise ANDing it with a generator of a bit shifted or divided square wave. Then doing a bitwise OR of all these 3 things in the top parenthesis, and combining them together so that all of them get played at the same time, and then subtracting one, and you'll hear why here for the snare. So now you have heard some multi-track, multi-tonal bit shifting music, but the interesting thing is the -1, because it means we have a new musical primitive, because when the waveform hits the bottom naturally and we subtract 1, we have an underflow and we suddenly have a signal spike. And because that only occurs with the period the original music has, and because it previously hits 0, if we subtract 1, we have a beat that fits perfectly to the music for free. And besides that, there's also cheating. I showed you the pitch table, and once I built this, which is a simple program which interprets a string, or well, several strings, based on the time, and in the end divides by 0. And if you actually take this apart, you see I've cheated, because what I've done is taken an index of the string I originally had, and used the characters, like the AND character, the parenthesis, and the star, and the comma, and the dollar, as different pitches into a wave that it generated based upon the time that the counter has reached. This is not what I wanted to do because, so I'm just recreating a really, really bad tracker. So use SIGINT track for that or something. If you want to make the music in style of Unreal Tournament from 1999. There's a paper that Wisnut has written discovering novel computer music techniques by exploring the space of short computer programs. And I suggest, if you want to know more about the math behind that and about the musical primitives that you can use, you read that paper. I got to that shortly before I wrote that paper, but in the meantime, what he has not done is identified problems, and there are problems which are pretty relevant to this audience, because there is an insecure composition exchange. Would any of you, run arbitrary C code I sent you if I said, well, it makes really cool music? How many of you have got Flash installed? Oh, you. If you're not willing to run arbitrary code, C is out of the window. You cannot do that because it's insecure. And we have something that I call the halting problem of sound synthesis. Will there be a next sample? If so, when? I mean, to have not, if the bit stream stops, we have an audible stop. And this means that people who do sound synthesis in real time actually have to make sure that there can no endless loop and that you have no insecure memory stuff and all this thing that you get with, well, the last thing is infix notation, because how can I do live coding? Let's say I have something that allows me to only input the formula and I say T, and then I say T plus, and the program does not compile, even if it gets compiled several times a second, and immediately the byte stream gets written to DevDSP. At this point, the program stops. This is a syntax error. We cannot have this, so we cannot do live coding in C as well. But the language theoretic security to the rescue, if we just adhere to simple principles of the Lang sect, no Turing complete input languages, no C, and full recognition before processing, we can avoid all of these. And this means that if you just go read Patterson and all the paper that the Lang sect people have put out, you can apply their security notions to musical composition, and especially how you synthesize a language should look. And because of that, I wrote something that I call the glitch, which is named like a similar lib glitch which does OpenGL stuff, which is unfortunate because I did not know about it when I wrote it. And so it's not the lib glitch that you can see in your package management in Debian. The other lib glitch only concerns itself with visual stuff, OpenGL and so. And once I met the authors of those and they were drunk and we discussed merging it to ease confusion, but then I thought it was even more confusing. So on this URL, you can see the source code for it. It's written in Python, and I'll probably provide it somewhere else because GitHub stopped working without JavaScript. libglitch interprets a serialization format for this thing. This is pretty unreadable for you unless I explain it. And this is the song, the multi-track song with the snare that I showed you. And the first thing, Rolling, is the title of the song. A guy called Matt Garden wrote this. Not this code, but the original song in C. And the exclamation mark denotes a new line. It's just syntactic sugar. But something like A9, A is the opcode, because this is an actual language. A is the opcode for put T on the stack, and 9 is put 9 on the stack, and D is the opcode for bit shifting. I've written specification for this. You can see it in the repository. But the interesting thing is with that approach, you can actually do live coding. You can actually have something because we have postfix notation. It's similar to Forth, if someone of you knows Forth or has, I think, an HP calculator. I don't have anyone, any HP calculator, and I don't know anyone who has. You can write T and then T plus, and it's not a syntax error because T means put the counter value on the stack that you have. And stuff like plus or the star like multiplication just means consume items from the stack and multiply them and put the result on the stack again. We can never have syntax errors again if we just look how our programming language is abstracted. Of course, we get different errors, errors of intention. We have no parentheses anymore, so we need to be careful. This all runs on a one stack machine, which I believe is not Turing complete. I actually have no idea what I'm doing, but I can guarantee that the code, if it runs for one value, terminates because this line is introduced from the first exclamation mark rightwards, and every opcode is evaluated once, and after that, on the top of the stack, I have the value that I want to output to def DSP 8,000 times per second. But if you divide a second through 8,000, you see that there's a very small window of time that I have to hit, in which I have to even include the output from the last calculation, so I can't actually really do it in batch, because if I pre-calculate too much, there is no longer live coding. And if I pre-calculate not enough values or my computer is too slow, then I'll get audible gaps in the audio, in the music. So going from that to another thing, like you see T and plus means consume 2 items from the stack. So, oh no, after I've consumed T, the stack is empty. There's an easy solution. The stack is a ring buffer, and a ring buffer means that when I consume something from the stack, it not only goes into my working memory, but also gets put below the stack and appended there, and the other way around. If I put stuff on the stack shifts around. It has always a specific size, which eases something, which eases the thought model because there is no empty stack. And there is no full stack, and you don't have to keep track of elements on the stack, but only have memory and a pointer to a location in the memory which represents the top of your stack. And I can also display this stack with libglitch. Now a live coding exercise because I both need this and haven't finished my presentation to that point. First thing, in C, I've written something that is called algorithmic symphonies, and there I have a script called play, which outputs, which just wraps this formula with C code and plays it. And this, I hope some of you can read. I can make the terminal bigger. I hope. I have no idea what I'm doing. So in case any one of you can read this, the formula at the top is the formula that I showed before. There may be something missing. Oh, yeah, the left part of the screen is missing. Now so this is the formula I've shown you before, and a script called play wraps this with C code and compiles it, and it hex dumps it to the screen so we can actually follow the waveform. It doesn't work. It doesn't work with this font size, so I'll just make this. Sorry, what? Or just use a system fixed font. Again, and meaning you had an audible gap. And I can have even more stuff. For example, music that plays more, there's more techno like. But this is all the original C code, but libglitch is different. With libglitch, I can have the rolling track, I can do live coding. You've seen this thing, and you've seen the opcodes for it. I can change stuff. And you can, in the bottom right corner, you can see the value that is there. But what I've also done is I've displayed the stack. Because this is the stack consisting of 16 times 16 values. And it's a ring buffer, and you can see how the music goes. And I use the first 12 bytes as hue, the next 12 as saturation, and the last 8 bytes, which get output, as value, so I have colors and stuff. And I can do pretty weird stuff with that. For example, trippy music. If I change this, you can see how it goes. This is the stack of the virtual machine I'm programming live here. So if any one of you want to go program drugs, use this. This is the thing I'm feeding it with. And it outputs the code that you can share with other people so they don't have to introduce insecure C code, sound synthesis into their system. So the interesting thing is that you can actually do stuff like low fidelity speech synthesis thing. I haven't figured that out. This song is from someone else. It's called Star Lost because but interesting is that it's a very short formula, and you can also go from the original stuff, having the original wave, putting it on the stack. You see at the left, you can see the waveform that I'm generating, and then iterating and putting ST on the stack again. And then I can do another thing where I bit shift it by a farther amount. T on the stack again. This is too much. This changed slower. And now I can combine both of these. And make fun patterns in memory. This is a knot. You see the signals cancel each other out. You can probably generate a triangle wave that way. This is a bitwise indication, I think, of the signal. And what if I apply both to each other? You can see I can modulate one signal on the other. Like one signal, usually the one with the lower frequency, which if you make it inaudible, doesn't even disturb anyone. I'll pause this. Can be used as a carrier frequency for the other signal, and modulate it. And for example, you can first program a beat, then slow it down so it's inaudible, and then make a bitwise and with the actual melody that you. How many minutes? I can't read this. 5 minutes. Okay, 5 minutes left. I'm nearly finished. There is, there's one thing that virtual machine format came from someone called McGarden, who made an iOS application, which has a very dumbed-down interface. But before the application was put into the App Store, he kindly shared the header files, and I made a clean room implementation, which is this lib glitch. And I would like to, if you would like to read more about this, go to this site or search for ByteBeat, because this site contains many links also to the archive paper. And also, please try to compose music using that. Not in C code, but with a dumbed down, not too incomplete language. It doesn't need to be my own, but try to do that, because as I have, I've never held this talk before before an audience so big, but I've asked many musicians and sound technicians, and many people aren't able to try and get rid of the notion that you need an instrument, because they can't think of a waveform generator as something that is musical. They can only think of a waveform generator as something, and with it I will end my, something that can be used as a primitive to put notes on it. This program does coupled strings and synthesis, and this is a pretty old technique, I believe. But what you can see is that in this case, I'm only simulating how the actual vibrations from the guitar are, because what I'm doing is translating the physical thing. I need to get the original program. I use a generator to generate noise, which is I think the top line or the top two lines, and then I get a value from the stack, and because the stack is a ring buffer, this is a value back in time from earlier sampling, which I output, and put it through a modulo division, which means there's a low-pass filter, and then I have the attenuated signal from a few milliseconds before, and multiply it and combine it with the original signal back, which means that I have a big vibration, the noise at the beginning, which goes, which slowly tapers off, and this is the actual physical movement of a guitar string, I think. But the point is, stuff like that is how people who write synthesizers think about it, and I'll urge you to try to think different in very wide sequential counters, which just generate a waveform, which is the music that I'm talking about, and use C compilers only on your own system for composition. Yeah, thank you. I'm done. Questions? Yes? Well, can you repeat that question? Yeah, the question is if human beings work according to simple mathematical relations, and I think my personal answer is that it's very easy to produce binary relations and binary rhythm with that, and because Our strongest enemies for every single one of us are two-legged creatures. I think it's very beneficial for humans to be influenced by binary rhythms and stuff. I've considered this, but this is no more than crazy talk when sleepy, so I do not know of any research into that. Another question? Can you speak louder? Can you come here and talk into the microphone, because otherwise I would have to repeat that question, and we don't have much time left.
Okay, actually, if you have a note, you have a base frequency and upper tones, which are integer multiples. And actually, I think in your formula you showed with the bit shifting, you had these things. You had the nodes and loop and the sequence, because the modulo operation combined with the sample rate, that's a loop and a sequence. And also because of this relationship that you have a base frequency and integer multiples. So if you do a bit shift operation, it's a multiplication with an integer. And so you have also nodes in that. So that follows the normal.
I know that it actually partially reproduces the prevailing concept, but you can also have entirely different generators which do not build upon a square wave, which are just noises or other fractals. Yeah. So the point is not going all hipster and Arch Linux and throwing out away everything that is there, but not being limited by the way that we think about music when making music, because we have entirely new tools which are, even if they're not Turing complete, more powerful than a guitar.
Yeah, I would.
Yeah, and
but actually, a guitar is also a mathematical device, because if you divide the string,
take the half of the string,
the
frequency changes. Right. But the point is, people aren't actually, even if they learn that in school or in university, they aren't actually paying attention to this when they make compositions.
Yeah.
Yeah. So anything else? So yeah, thank you. What? Yeah, as every time there's also an insecure JavaScript implementation that will probably ruin your life and expose you to the secret police. JavaScript is not good for crypto or audio systems or anything at all. Don't do that. At all. No Turing complete input languages. It also has infix notation, so it has the same weaknesses as the C implementation, but it's JavaScript.